Welcome everybody. So this is the last lecture on coding and milestone 4, and won't even take the whole lecture. So I'm going to quickly introduce you to multithreading. To learn more about this, either go to, or if your tutorial's already happened, watch the recording of the tutorial this week. So we go into multithreading more in that tutorial. I'm just going to kind of give you a teaser of why this is interesting. Okay, so multithreading is making a program use more than one core. And as I said, in the tutorial we'll teach you how to do that. I'm going to mostly motivate what is the purpose of that. So this is the first, whoops, that didn't work too well. Let's try that again. This is the first PC microprocessor, the Intel 8088. It was shipped in 1978. It had 29,000 transistors in it, ran at 5 megahertz clock frequency. You're learning about instructions in ece243. So in this microprocessor, to complete the typical instruction would take 10 clocks, right? So you'd decode what does the instruction mean, fetch the operands from the register file, execute over several cycles what you want, write it back, okay? So that would take you 10 cycles. If you work that out, that means that this could do about 500,000 instructions per second. Okay, so let's fast forward to today. In the UG machines, the CPU, the processor in there, is a chip called, it's an Intel Core i7 chip. Now, Core i7 doesn't mean much, right? It's kind of a marketing term. You'll find lots of processors that are called i7s, i5s, etc. So what really is more meaningful is actually the internal code name, what's called the microarchitecture from Intel. This one is called Rocket Lake. So if you actually want to go look up more about the CPUs in the UG lab, go look up Rocket Lake. But I already have done that. Whoops, let me stop doing that. It has about 5 billion transistors. Okay, so we've gone from 29,000 transistors to 5 billion. The clock frequency is not 5 megahertz. It actually is variable. It's a big challenge nowadays to control power dissipation on chips. So the clock frequency will actually go up and down depending on how hot the chip is running. But it basically goes from 2.5 gigahertz to 4.9 gigahertz, depending on how cool the chip is. Much faster than 5 megahertz. It actually takes about 15 clocks per instruction. Okay, remember that 8086 took 10 clocks per instruction. So part of how we're clocking this faster is we're dividing up what we do into small pieces. So it takes more clocks per instruction, but each clock's much faster. But this processor doesn't work on one instruction at a time. It's actually working on about 45 at a time on average. So that means even though each one of those 45 instructions takes 15 clocks to complete, because I'm working on 45 of them at a time, on average this processor, a core of this processor can complete 3 instructions per clock cycle. So if we multiply all that out, we get about 15 billion instructions per second per core. Much, much faster than we had back in 1978. And then we also got something else. That chip in 1978 was it was a single core processor. Nobody even would call it a single core processor because that's just all there was. It was one CPU. The chips that are in the UG lab, what I've drawn in red here, are the 8 cores. So they have 8 of these processors on one chip, and they actually have more. What you have over here is actually an integrated GPU as well, and integrated I/O for PCI Express and so on. So there's actually a lot on this chip. But the part that we really care about is this part. That's one core. There are 8 of them. Okay, so what's happened in CPUs over the last, how long is that? I guess more than 30 years. So we got 170,000 more transistors from 1978 to 2022, because that's when the chips in the UG machines were made. And we got 30,000 more instructions per clock cycle per core. So huge improvement. In the future, we're still going to get 2 times the transistors approximately every 3 years. That looks to be still the case for the foreseeable future. But transistors are not getting much faster. In order to control power, we basically have to make trade-offs in the transistor design. Also, wiring is the resistance to the wiring limits us more than it used to. The net impact of that is that the clock speed of CPUs is not changing very much anymore. It's been around 3 to 5 megahertz for a while. It's kind of slowly going up and not much. We can do more instructions, have more instructions that we're working on. So we're working on 45 instructions at a time right now. You can take that higher, right? You could work on 55, 65, 75 instructions, but actually the complexity of this rapidly increases. Maybe you will learn more about this if you choose to in 4th year. The complexity of how do I find all these instructions and work on them at once, and it's invisible to the programmer. Programmer doesn't know we're doing this. They just write one instruction after the other. It's really hard. So we can't go too much higher than 45, but we'll go a bit higher. Okay, what does this mean? It means that CPU cores are not getting that much faster. They're getting a little bit faster at running a program, but not nearly as much faster as they used to. But we still have way more transistors every 3 years, twice as many. So what we can do is we can put more cores on a chip, and that's what all the processor vendors are doing, right? Whereas you used to get one CPU, now you get several. When you buy a laptop, you get maybe 4, even 8. When you buy a server, you're getting maybe 32, maybe 64. Okay, so how can we use these chips that now have multiple cores on them? Well, one way is to run multiple programs, and that's why in the UG machines, usually you don't actually notice a lot if there are 2 or 3 or 4 students on the machine, because there are 8 cores, everybody gets their own core, you're all pretty happy, okay? So the operating system can basically share, the memory is physically shared amongst all these cores, but the operating system can basically chop it up. And if you've got multiple programs, it's actually exactly what it does. Everybody gets their own piece of memory, you don't interfere with each other. Try to go outside your own memory, operating system kills you, and you get a seg fault, all right? So you already know how to program one of these cores. But what if I want my program to go faster? I don't want to share it with 7 friends. Now I want to have one program that tries to use all of these cores. And that's called multi-threading or parallel programming. When we do this, basically each core will be executing, they're all running the same program, so they all see the same instructions, but they all have their own program counter. They're all executing a different part of the program. Each of them has its own stack, which means they each have their own local variables, but they all see a shared memory that has global variables and basically all the objects that were created with new and that you have a pointer to. So they can share data very efficiently through this shared memory, and they can all be executing different parts of your program. Okay, so I went through that really fast. We talk way more about this in the tutorial. Basically, this shared memory model lets them talk to each other really quickly, but you have to be aware of it, because you can also now make a program that does not work. On the UG machines, if I run this command, ls CPU, it'll print out a bunch of information about the CPU. 2 of the things you'll see it tells you is, well, the most important one is it actually tells you that there are 8 cores per socket. Socket means computer chip, so it's telling you I have 8 cores in this processor. It also tells you that it can actually run 2 threads on each one of these cores. So a thread, again, is like it's an execution unit. It's a part of a program. So far, all the programs you've written in U of T have been one thread. So you never really thought, what is a thread? Thread and a program seem like the same thing. So the UG machines have 8 cores, and then each core can have be doing 2 different things at a time with somewhat reduced efficiency. Basically, modern processors have many execution units. It can be hard for one sequence of instructions to keep them all busy, one thread. So they can run 2 threads at the same time, and they'll interfere with each other some, but you can sometimes get some extra work by doing this. Okay, so that's what you've got on the UG machines. For your milestone 4, what matters the most is actually number of cores. So you can get, if you actually manage to take your program and turn it into a multi-threaded program, you can actually use all 8 of these cores, and you can get some operations done about 8 times faster. Okay, so what should we multi-thread? Actually, let me see if yeah, okay, sorry, I'm forgetting the order of my own slides. So I'm demonstrating what not to do in op2, where you haven't practiced quite enough. Okay, so I haven't told you how to multi-thread things yet, but multi-threading is a programming technique where you can split work across multiple cores. It is more complicated, right? So this is considered a more difficult programming problem. It's becoming increasingly important. The reason it's increasingly important is we can't make CPUs much faster anymore except by making more cores. So we don't want to just go off and try to make multi-threading everywhere in our milestone 4 program, because it'll be a mess, probably won't work, there'll be sadness, there will be bad course evaluations, no one wins, okay? So don't do that. What we want to do is we want to think, if we multi-thread, you don't have to do this, we want to find something that takes a lot of CPU time, because then we're going to have the potential to get a good payback on the extra effort we're going to put in to make this software more complicated and use multiple cores. So it has to be something that takes a long time. Secondly, we want the work to be independent. Okay, what I mean by that is, I'll show you maybe a quick example, but mostly this is going to come in the tutorial. To make the cores collaborate, you want them to each be doing things where they don't have to be communicating a lot. They don't have to be sending each other data. The reason is that's slower, so it's going to slow them down, and it's also harder to program. If they have to share data, you have to do it in a very careful way or your program won't work. So we want to try to find things where they just don't have to share much data. So what are some candidates? The obvious one, and the one we're going to do in the tutorial, is pathfinding. Okay, so I've shown you that you can get better results if you actually get sort of the truly accurate travel times between the various delivery locations and use that when you're evaluating what order you should go through things. And we talked about how we can do this algorithmically reasonably well if we use a multi-destination Dijkstra. But even with a multi-destination Dijkstra, if we have k intersections that are involved in our courier problem, right? So, and for the biggest problems we give you, k is like 375 or so. So it's a lot of intersections. We have to invoke our multi-destination Dijkstra once for every single one of these intersections. So from this starting one, tell me the travel time to all the others. And they're all doing independent work. Each of those do a path search starting from this intersection that is completely independent of do a path search starting from this other intersection. There's no dependency, they don't have to exchange any information. That's good, makes it much easier to put this in different threads. It also, on milestone 4, you'll find that this is usually the biggest consumer of CPU time. I show this in the tutorial, but basically in our reference solution for the biggest problems, we will use 40 out of the 50 seconds that is our time budget to do this pathfinding. Okay, so it takes quite a while. So that's a good candidate. Another one you could do is you could say, we talked about multi-start, right? You can take an algorithm that you already have, and you can start it from multiple starting points, change something. That also is pretty independent. You already have the algorithm. If you just change a starting point, you could give each thread a different starting point and say, go run the same algorithm. We'll get all the answers, and then afterwards we'll look at which of those answers was the best, and that's the one we'll return. And there's, again, not a lot of communication there. There is a little bit. Like at the very end, we need to look at all the answers and decide which one's the best. But in between that, we didn't have to make many code changes. So that's another good option. Another thing that you might consider is, well, we have these perturbations that we can do. And you could say, well, when I find a good perturbation, maybe I could have multiple threads, each trying different perturbations, and then maybe when they find a good perturbation, they'll tell the other threads. So they all update to, I found an improvement, build on top of that. That's a bit harder. It's doable, but if you want them to communicate the best perturbations to each other as they're running, you need something that we talk about in the tutorial called the critical section, which basically allows them to safely exchange data. So basically, this is your kind of best bang for the buck. Takes the most CPU time, and the work's truly independent. As we go down this order, the work actually gets a bit harder to organize. It's less independent, and probably you also have less total CPU time that you're going to gain back. Okay, how do we do this? This is a super brief overview. I'm going to go to tutorial 8 for details. There are 2 dominant ways that people use multiple threads in C++ programs. So maybe I'll start with the bottom one. The bottom one is if you go look on C++reference.com, you'll find that there's a header file called thread, and that is an API to create and manage threads. Basically, when your program starts, there's always one thread, and it starts running main. If you want more threads, you have to create them yourself. You can do that with this threading part of the standard library, and that can be useful. So what I've given as an example here is how you could actually create threads in order to make load map faster. So we can divide load map into two parts. One part that loads all the OSM kind of lower level data, and one part that loads all the streets database kind of higher level data. And we can actually make load map run faster that way, and it's not too hard. And that fits reasonably well into this style of coding, where you create the threads yourself, and you basically tell them, start running this subroutine, and you start running that subroutine. So here's an example. I talk a little more about it in the tutorial. But for milestone 4, what we recommend is if you want a multi-thread, you don't use that lower level API. You use a higher level one called OpenMP, or Open Multiprocessing. Basically, for that, you can just take for loops, for example, and you can put a pragma, that's a directive to the compiler, that says, I want to take the work in this for loop, so as many iterations as this for loop. I want you to split up those iterations, create a thread for each group of iterations, and farm out the work, and then when all of the threads are done, all the cores are done, you can continue on to the rest of the program. It basically is creating a bunch of this. It actually does this by automatically creating a bunch of this lower level threading code, but it's basically easier. You don't have to write as low a level code. And we go through this in the tutorial in kind of great detail. How can we do this for like some simpler programs? How can we do it for the pathfinding algorithm of milestone 4? Okay, so but it's going to be harder, right? You're going to wind up putting extra effort in this, so what could be the payoff? Let's say that I spend 75% of my time in my program doing this pathfinding, right? Finding all these travel paths between intersections. And I spend 25% of my time actually trying to choose the order of intersections. And this is pretty reasonable. This isn't too far off what our reference solution does. So then that pushes me towards, if I'm going to use multi-threading, I should take the biggest CPU time block and try to make it parallel. And I want to know, well, how much faster could this whole program get? And people usually define, in parallel programming, people define this term called speed up. And all speed up is the amount of time it would take you if you ran your program on one core, divided by the amount of time it takes when you run it on all of the cores, say 8 cores in this case. Okay, so, and you can compute, if I assume that I can perfectly split this pathfinding up, I got 8 cores, and if I split the work up perfectly, that pathfinding is going to run in 1/8 the time. I can compute what speed up would I get. Okay, so I've got 0.25 is the time that's path ordering, like intersection order, so I'm not changing that. But this 0.75 is my pathfinding time. Okay, so my serial runtime is just 1. Right, 0.25 plus 0.75. My parallel runtime is the 0.25, because I'm not changing that. My intersection ordering code is not changing. But the parallel pathfinding, I'm assuming this 75% of my time will drop by a factor of 8. If I plug all these numbers in, I get a speed up of around 2.9x. And this is kind of a guaranteed not to exceed number, right? Maybe I won't actually get 8 times the speed up due to some non-ideal effects. Turns out you can get pretty close to 8x on this parallel pathfinding. So we'd get a speed up of about 2.9x, which is pretty good, but you notice that it's not anywhere near 8x. And this is a standard thing that happens all the time in parallel programming. It's given a name, Amdahl's law, after Gene Amdahl, the mainframe computer pioneer. And basically, you can't get a bigger speed up than the fraction of your code that is serial. So because 25% of my code is serial, I can't ever do better than 4x speed up. Even if I made the parallel code run on 1 million processors. I didn't actually get all the way to a 4x speed up, I got to 2.9x. So Amdahl's law is a useful thing to know, to work out, is there enough of the work that's parallel that is worth my effort to program this? Okay, so my advice on milestone 4 is keep it simple. I've described multi-threading because it's a very useful thing to be aware of, and you can employ it usefully in milestone 4, but don't try it until you have a good serial implementation. It is fundamentally harder to write, it's harder to debug, and one of the things we've tried to teach you in this course for project management is get something working, because almost all projects in both school and industry run at a time. So if they run out of time and you've got a pretty good solution, it's fine. If they run out of time and you've got like a broken, was going to be brilliant, but is in fact just not working at all solution, life is really hard. And it's really hard in industry too. So this is an important lesson. Like in industry, it's actually much harder. It's much worse. So it's an important lesson to learn. So get a good serial implementation going. It is a lot harder to write and debug multi-threaded code. You don't need a multi-threaded implementation to have a good implementation. So again, in the tutorial, we go over that algorithmic improvements are more powerful generally than parallelism. So parallelism is useful, but getting a good algorithm is even more important. So you do not want to spend a bunch of time on parallelism without having a good algorithm. And you can get a good result on milestone 4 without parallelism. So you can also just say, I'm busy, interesting lecture, I remember, on to the next course. That's totally fine. Okay, a few resources on this. Tutorial 8 is the big one. View it or go to it if you want to know more about this. There are also detailed tutorials online on OpenMP and on how to debug with multiple threads. I show some examples of this in the tutorial, but basically debugging is harder with multiple threads. You actually now have multiple call stacks. You basically have different threads are in different parts of your program. So it's a bit harder to think about, but the debugger GDB, which VS Code and NetBeans talk to, does handle multiple threads, can help you. Okay, so that's it for milestone 4, parallelism. Any questions on that? I'll give you a second, I'll pause and ask if anybody has any questions. Okay, so if not, I'm just going to highlight a few course links of things you might want to explore after this course. So, performance and multi-threading. So if you like making programs go fast, ece297 is all about how to make programs go fast. By profiling them, which we talked about, but you do more of it. Writing code that a compiler can turn into efficient instructions, so you kind of learn more about, well, what do I write in C++ or C that turns into efficient machine code? And parallelism, right? So going further in multi-threading than we are here. ece344 will teach you how does an operating system actually run these different threads? What's really going on under the hood, which is pretty interesting. And ece552 is computer architecture. So how do we make CPUs faster? How do we make one core faster? How do we make multiple cores communicate well? If you liked graphics, so we talked about graphics in this course, computer science has ece297, which actually talks about how do graphics renderers work. So how do we go from a high-level description to pixels in 3D, which includes, so it's not only 2D, it goes a step further, how do we do that in 3D? And ece444 is software engineering. You pick a project in this course, most of the projects include some kind of graphical component. So if you like building user interfaces, you could choose to have that opportunity there. Okay, let's say you liked working in projects and teams. So APS 111, 112, taught you the basics of working in a team, and it tended to be, it's kind of changing I hear, but basically it tended to be more specification driven, so pushing you a little more towards waterfall development, although I hear it's getting more agile in recent years. So we've emphasized agile development, and we go further in implementation, and we also emphasize measuring. In software engineering, you would build on that. You'll work in larger teams on a project where you not only implement the project, you define it. You'll use tools like Git and so on, so you can keep building on your skills from here. You're definitely going to do a capstone project, and in that you're not just going to implement the design as you did here. You will specify what is the overall project, so you're kind of going to the next level. What is the problem? If you are interested in just leadership, team dynamics, how do we make them work well? APS 343 is about engineering leadership, really important skill in industry, and iLead has a bunch of project management and team management workshops where you can kind of hone your skills in that area. So with that, I am done. I'm going to hand it over to Professor Chong.
Just one sec here. Oh, it sounds like the mic is working. All right. Okay. All right, everybody. So congratulations, you guys are almost done your ece297 course. I know you guys are having your last CI meetings this week and your final tutorials, and we don't even have to really worry about that op2 for quite a few weeks, okay? But we unfortunately can't schedule lectures close to the op2 date. So I have to go over the key things I want you to know for that oral presentation over the next 2.5 lectures, okay? And essentially what I want to do in the next couple of lectures is to kind of deepen our understanding of some of the oral presentation principles that we talked about. I want to take you through that planning and requirements gathering phase for op2, just like we did for op1. And then what I want to do is to kind of get into a slightly new part of op2 that you haven't done before, which is this idea of the pitch. And the idea of the pitch is a really important skill for your career because it's something that you're going to have to learn how to do effectively if you are an entrepreneur, if you've got some ideas that you want funding for or time to work on. And so I think it's a good thing that you have at the end of this course to kind of work on as a communication tool as well. Okay, so today we're going to focus on kind of debriefing op1 and kind of deepening our understanding of some of those things we've already talked about, but we'll talk about in a slightly different way. It probably seems like a long time ago, but op1 was only a couple of weeks ago, right? It was only 3 weeks ago. And what I did want to say is that we, as a team, assessing the presentations, were really impressed by the quality of work we saw in op1. Now, we realized you guys had a bunch of deliverables at that time. It was a really tight time frame, and you turned it around really well. So especially given your constraints, we're really kind of impressed by what we saw. Now, one of the things that we do want to talk about is that you should have a ton of feedback from op1, right? You should have had the discussions that you had in your CI meetings. You would have had the formal feedback from your CI. You would have had your peer feedback. And what I think, what I want to emphasize is probably the most important thing is you have the experience of having done op1, right? And for a lot of you, I think that involved doing a self-reflection in your CI meeting. And I think that self-reflection is very valuable, right? It helps you to kind of figure out, what your strengths are yourself, and now you can talk with your CI about how to overcome some of those concerns. I did notice that a lot of you were some of your own worst critics, and in fact, a lot of the things that you were really concerned about were not as big of a deal, and there's small things that you can do to kind of work on those skills and improve them. Okay, so, the last thing I wanted to say is I know some of you and not all of you had the opportunity to view yourself on video. Those of you who did, I know it's not a very comfortable experience, but it's also a really good experience for you as a learning experience because it really does allow you to see what your strengths and your weaknesses are. Okay, so today what I want to do is kind of reinforce and deepen some of the concepts that the CIs identified as being really important to improving for op2. And the things that we're going to focus on are 4 main things. Number 1, we're going to talk about framing a little bit. We're going to talk a little bit more about slide design. We're going to talk quite a bit more about delivery because I think that's one area that we didn't get to cover very well before op1, and then we're going to talk a little bit about practice as well, okay? All right, but I'd like to do this by giving you a slightly new perspective that I hope will help us understand why we want to design and deliver our communication in a very specific way. okay? And that's cognitive load theory. Okay? And cognitive load theory is used in kind of pedagogy and educational theory, and it's all about how an audience receives and processes and retains information. Now, there's a lot in it about working memory and long-term memory that I'm not going to cover, but essentially what it says is that when we're hearing or when we're learning about something new, such as in an oral presentation or in a lecture setting, for example. So a lot of people use cognitive load theory in planning educational interventions and classes and things like that, okay? We're doing a lot of expending energy trying to process the information that we're receiving. Okay? Now, cognitive loads then are things that have an impact on the amount of mental activity or energy that needs to be expended or carried out by working memory in order to perform a specific learning task, okay? Such as learning about your GIS design or your algorithms or its performance, okay? Now, research has identified 3 types of cognitive load, right? First, we have this intrinsic cognitive load, which is just the plain complexity of the information being delivered. Now, you have some control over this, but you don't have a lot, because obviously the type of material that you're going to deliver as an engineer, it's going to be complex, right? It's not going to be straightforward and simple all by itself, okay? You do want to simplify as much as you possibly can and kind of manage this level of cognitive load, but it's not something you have complete control over, right? Now, there's also extraneous cognitive load, which are any of the external factors that you do have control over that would distract working memory from processing new information effectively. Okay? And this is one area that we definitely want to minimize. We want to kind of minimize this level of extraneous cognitive load. We want to work to understand what introduces this sort of cognitive load into an experience of a document or an experience of an oral presentation. We want to target that pretty carefully. Okay? And then finally, there's this idea of germane cognitive load. And these are factors that allow for the processing of new information by linking it to old information or information that we already have, okay? So this is something you want to kind of maximize, or you want to kind of create as much germane cognitive load as possible so that they're making those connections to existing memory and existing knowledge, and so they're understanding how the new knowledge that you're introducing fits into all that, okay? All right, so these concepts, right? You want to maximize germane cognitive load. You're not really minimizing intrinsic cognitive load. You're more like managing it, but you are trying to minimize extraneous cognitive load, okay? And why do I want to introduce this? Well, essentially, I want to make sure that we're using it to help understand how people receive new information and how to design our information so that we can maximize your ability to understand and process that information, okay? You might also notice that this slide is an example of the assertion evidence model where I've just thrown in the assertion. That is also another way of managing cognitive load, right? To kind of create that germane cognitive load as well, okay? All right. So let's walk into some things around our oral presentation skills that can help us kind of work effectively with cognitive load, okay? So one of the things that we can do to increase the germane cognitive load, okay, is by properly framing our presentation. Now, I spent a lot of time talking about how to properly frame that presentation before OP1, and it's that job of setting up the presentation in a way to create all those links that connect all the material that you're going to be providing in the presentation to a kind of core idea and kind of creates that coherent thread throughout the presentation, right? And this was identified by your CIs as a really core and key element of the effective presentations in OP1. Right? Starting with a really clear core message at the outset, preferably, hopefully they applied some of the made to stick principles, being simple, concrete, and credible were the kind of main ones that we were talking about at this point. And we want to be able to create a core message that is sticky, that we can remember, and that we can use to center that whole presentation. Now, we saw a bunch of types of this type of core message, right? We saw things like, our UI is usable and responsive, okay? And again, we talked about how this wasn't really much of a core message at all, because all it did was really restate the assignment statement, right? It doesn't give you anything to kind of go with and focus your attention in any sort of way, okay? Something like this, our UI is clean, clear, and comprehensive. Okay, those are 3 keywords that I can kind of stick to in terms of my understanding of what your UI aspires to, okay? And it's simple, okay? But it's a bit abstract, and it's difficult for listeners to relate to and immediately tie into. And remember that statement from made to stick: if you've said 3 things, you maybe haven't said anything, okay? As we develop a little bit more focus and clarity and stickiness in our core messages, we saw that they were grouped around 2 sets of things, right? Either a group of potential users, okay, or a design principle. And so a user might look something like this. We've designed our user interface components to prioritize and highlight information that's most needed by tourists, right? This is a little bit more concrete of a statement, easier to understand and connect to, but it's something that could be reinforced a little bit more by potentially a story or an actual description of what these tourists would actually need in this particular situation. Okay? And the other kind of structure, the other type of core message that we saw a lot of that was quite effective was this focus on a specific design principle. So here our graphics have been designed around Jakob Nielsen's usability heuristic that states when design is predictable, it is most usable, okay? And there's a piece of, there's a core message that brings in external credibility, right? It brings in a source. But it's something that could potentially be a little bit more concrete or made more concrete by detailing how user experience would link to that, okay? So when we're constructing our core message, we do want to think about how all of these things connect to some of the principles from made to stick. And like I said, I think the ones that you should be really shooting for in creating your core message are simplicity, concreteness, and credibility. Things like story, unexpectedness, and emotional. These are also good principles, but they may be a little bit more difficult to tie in, a bit more risky, but they could have a potentially high payoff as well, right? So the first thing we want to do is we want to make sure that that core message is something that is very clear, clearly articulated, and compelling, right? And once we have that, we can start connecting all of the facts that we have, all the information that we have in the presentation to that initial piece of information, okay? And then by doing that, we can kind of limit the amount of we can maximize the amount of germane cognitive load we're introducing into the presentation, right? So we want that core message to be clearly identified and motivated in the introduction. As you're developing your overview, we want your description of the graphical features or the algorithmic features or aspects of your GIS that you're going to discuss to be tied to that core message in the presentation overview. And as you're going through each of your graphical features, all of these are going to be tied back into that core message, right? And essentially, those things should all be linked to the core claim, kind of support that core claim, and we're using that core message to draw a straight line through that entire talk. And that's what is able to create that germane cognitive load that helps people process that information a little bit better, okay? The other thing to kind of focus on is, in terms of creating that germane cognitive load, is what I talked about in terms of having explicit structure and transitions made between each point in your presentation, right? And that's the connections drawing. That's the linking to old knowledge. That is really kind of, if you do it explicitly, it's something that helps us process all of that information, okay? So really key. I'm going to say a few things about slide design. What we saw in OP1 was pretty good. What I liked was that there was some additional experimentation and work with these components and relationships. So even in simple text slides, we were really starting to see that you were using different visual components to create relationships, even when just using text. So you can see in these slides there's a use of size, color, font size in order to create kind of different relationships between the ideas that are represented in the slide. So that was something that was good and something you should consider, right? We've got a bigger toolkit now that we know that we're working with not just a set of diagrams. We can kind of play a little bit with some of the tools that we've developed in terms of the components and relationships, okay? And then we saw that there was a start to kind of, you don't need to just have text, right? That text kind of reinforced with visual components can make for a much more effective slide. So even in things like the overview of a presentation, those visual elements can actually make a really big difference. Now, I saw a lot of people using a map metaphor and a visualization as we went through. That's also a good idea given it fits with the theme. But again, there are multiple ways in which to build both textual and visual components into the slide to make them effective, okay? But I will have to say, after watching about 20 of these over the course of those 3 days, the single most powerful tool or principle that I saw in effect in all of the presentations, like when I saw this in the slide, it was really clear that you'd used it, and it made a huge difference in my reception of that slide. And that was the idea of using that sentence assertion header to articulate that claim. So here we can see 2 slides, graphic draw times and responsiveness. What they might have looked like is something like this, right? Separating a GIS into different sections decreases the graphics draw time and increases efficiency. Again, I can look at that and very quickly process the message and the signal of that slide. And instead of looking at just responsiveness on the slide, maybe I can see that what I'm trying to see in that visual is that the grid-based data structure creates a responsive UI by preloading details at appropriate levels and minimizing data traversal, right? And so I saw a bunch of slides that had this sentence assertion header, and I saw a bunch of stuff that didn't. And I can tell you this was the one thing that made a huge difference in the impact of my understanding and my reception of that particular visual, okay? Again, even when we're showing just data of kind of task times or response times, you see this time with and without features. And this is a chart of users' time completing specific tasks with some features on versus some features off. Yeah, I can understand this, but if I'm given a title like this, our usability features reduce time to task, up at the top, I already know what I'm looking for, right? And I can see maybe a highlight of the detail that it's approximately 50% across all the tasks, right? And if I'm starting to talk about a very specific task, I'm gonna wanna highlight that data as well, right? So if you are, if your signal across the course of the presentation of that slide changes, you want to add those elements to highlight the specific data points in that slide, okay? All right, so a lot of good slide deck work, a lot of good slide work. Those things are the things that I would really kind of emphasize in delivery, in designing your slides for OP2, okay? Now, okay, we're going to step a little further into the concept of delivery here. And recall that when we talked about delivery, we split these metrics up into 2 key categories, right? One was basically, can we hear and understand what you're saying? And the other one was kind of more about engagement, whether I was enthusiastic or interested in the material, and so, and about your confidence and ability, right? So those were kind of the higher level ones. I will still say that we had quite a few of you speaking at too low of a level, okay, according to the CIs, right? I think volume was still an issue, and especially as you're moving to larger rooms in op2, that's something to consider as well, okay? Now, remember here that we are trying to limit extraneous cognitive load, right? And probably the biggest piece of extraneous cognitive load is an inability to hear what you're actually saying, right? So if you're at a couple of volume levels, right? If I can't hear you at all, I have nothing to assess, right? If you're speaking okay, but not loud enough, I'm working pretty hard just to process the information that is coming my way, right? And that means that you are introducing a fair amount of extraneous cognitive load on the listener, which means that they can't process that information as well as they should, as well as they'd like to, okay? And it also, I think, indicates a little bit of nervousness and a lack of confidence in your material as a speaker, okay? So we definitely want to get to the point where you're right at the right level of volume, okay? We can focus on what you're saying as opposed to trying to process what you're saying. And we can kind of focus on how all of the stuff that you're saying actually fits together and what it means, okay? I'm not gonna bother with too loud because I've really only made that comment once in 20 years. So it's not usually an issue, but obviously you don't wanna be too loud as well because that also introduces additional cognitive load, okay? So we wanna be here, right? We wanna be at the point where you can focus on what you're saying is fitting together into meaning and your core message, okay? And there's some strategies for doing this. I think Professor Betts probably has the best one, which is, a strategy that he uses at the beginning of every class. What is that? I'm gonna get, that's C6, sorry.
He asked if you can hear him before every lecture.
Yeah, every single class, right? Which is a really important thing to do. And here we're also asking for whether we're too loud because we're mic'd up, right? But that, that's not something that you necessarily are concerned about, but if you are concerned about whether you can be heard, that is definitely something you can do. Now, you'll do that at the beginning of the talk, and you don't have to always do that, but if you know that volume is an issue, that's a strategy that you can take to make sure that it works, okay? So ask if the audience can hear you, okay? But volume is also about projection, okay? And it's about kind of looking at projecting not just to somebody that you're looking at, somebody you're engaging with, but projecting past them, right? We want to get past the last person in the room. And to kind of do this test, I'm going to turn off my mic for the last few minutes, okay? And I want to talk about how projection really works, right? And how you're going to have to kind of focus on throwing your voice kind of past the last people in the room. Now, this is a big room. It's pretty hard to do. Takes a ton of energy from me, okay? But if you're doing things like turning to the side, okay, even if I'm speaking at the same level, the way that sound waves work, it's just not going to go to the right direction, right? And so you have to kind of combine projection with things